In this paper, we introduce ultra-detailed human avatars via multi-level surface alignment. Given ultra-high-resolution multi-view video captures for training. Our goal is to train a model that, at the test time, takes arbitrary skeletal poses as input and produces ultra-detailed human rendering, together with high-fidelity, consistent geometry. More importantly, our model allows users to zoom in and inspect the detailed textured patterns and geometry. Here, we show the results rendered with a spiral and zoom-in camera around the subject. Note that our model preserves large-scale clothing dynamics and delicate appearance details. Here, we show results for subjects performing novel poses unseen during training. Note that we can generate realistic clothing wrinkles while preserving the detailed clothing texture patterns. Given skeletal poses as inputs, our method generates photorealistic, clothed human geometry represented with topology-consistent meshes. Given novel poses unseen during training, our approach synthesizes vivid clothing dynamics and realistic wrinkles. We compare our approach against several state-of-the-art methods. Due to the inaccurate template surface tracking, deep dynamic characters and mesh avatar produces blurred rendering or fail to learn the wrinkle of the clothing. Tri-human, leveraging a deformable triplane sign distance field, reconstructs coarse motion-aware wrinkles, but still struggles to reproduce the delicate texture patterns on garments. As 3D Gaussian-based methods, both ASH and animatable Gaussians achieve improved appearance reconstruction. However, limited by inaccuracies in vertex and texel level tracking, they cannot faithfully recover the finest appearance details. For extremely loose-fitting clothing, our approach significantly outperforms the other 3D GS-based approaches in appearance and surface reconstruction. Furthermore, we compare our method against prior works in novel pose synthesis. Thanks to better tracked mesh and texels, our method produces more realistic dynamic clothing deformations and appearances. Bounded by the reconstruction accuracy during training, Tri-human fails to recover the finest levels of appearance details. Compared to other 3D GS-based methods, ours synthesizes richer wrinkles, sharper textures, and overall, more expressive dynamics across unseen motions. Given novel pose inputs, our method synthesizes geometry with richer, more realistic wrinkles. The generated result owns higher consistency and visual fidelity than News 2 trained separately for each frame. Tri-human, though capable of synthesizing some motion-aware wrinkles, fails to reproduce finer-level, detailed deformations. Given novel pose inputs, our method synthesizes geometry with richer, more realistic wrinkles. Our approach achieves substantially higher fidelity in synthesizing motion-aware wrinkles compared to Tri-human. For depth alignment, the baseline method produces noticeably blurred results, as it fails to account for the stochastic dynamics of clothing that cannot be modeled solely through skeletal motion. By introducing latent conditioning, the results improve quantitatively, however, fine details remain missing due to the lack of explicit surface correspondence supervision. Therefore, we address the correspondence supervision with vertex-level alignment. Simply applying a point tracker, however, leads to even blurrier results because of accumulated tracking errors. While differentiable rasterization provides slight improvements, it still struggles with the highly diversified shading variations. Our method overcomes these issues by coupling a foundational point tracker with a deformable template. Further, by introducing texel-level correspondence supervision, we improved appearance fidelity by tracking surfaces at the texture level. Finally, a lightweight Texel super resolution module preserves even the most intricate weaving patterns and faithfully reconstructs the tiny grid boundaries and weaving structures. UMA enables motion retargeting from a source character to others with different body shapes and clothing, while preserving realistic dynamics and fine-grained texture details. Since UMA produces ultra-detailed geometry with enhanced correspondence, it opens the possibility for consistent texture editing. Note that the augmented texture accurately follows the deformation of the clothing and is firmly anchored to the character's original texture. We developed UMA Viewer to inspect and create novel animations. Users can zoom in and rotate the view to observe characters performing existing motion sequences or design custom camera trajectories for rendering. UMA Viewer also supports intuitive keyframe editing for generating new motion sequences. Users can select the DOF to edit and efficiently generate a motion sequence for the DOF. Here, we compose the animation with 2 DOFs. Here, we show the edited animation generated with UMA Viewer. Note that the photorealistic, motion-aware, wrinkles on the pants and the pullover. UMA enables more immersive and enhanced VR experiences. Users can closely inspect the intricate texture details and subtle surface deformations of the rendered clothing. They can also zoom in to observe the dynamic geometry of the animatable character. Thanks for watching.